switch the measures so that formula is going to be nicer, things like that. Here's the beginning. So first, we're going to look at geometry problem. In that, it says geometry, and we're going to look at arc length and sector area, the circular sector area. Those are the formulas we're going to look at. It involves the idea of the angle, and then we're going to go to our circular motion. All right, and we're going to especially use the focus on this arc length. So those are the two applications they introduced at the end of this section 6.1. And when we do that, what kind of measure are we going to stick to, you think? It's going to be radian or degree. We switch to radian so that these formulas we use is neater than with degree, right? So it's going to be radian. So keep that in mind. That formula we introduced in here has to be applied to angle measure radian. The magnitude in radian is going to be used, but they give you information in degrees and things like that, and you have to switch to radian. So a first formula is this one. Here's the arc length of a circular sector. By using the word circular, it means very specific shape, right? Not just anything that's curved. You can't use this formula to anything that looks like it. So here is a center, and here is a perfect circle, right? Looks like a perfect circle. And here's the center of the circle, and then we have this subtended angle. Okay? So we indicate it like in the theta. So here I'm not indicating the direction, but just indicating what angle I'm looking at in here. There's no arrow in there. I just put the little arc there without arrow, right? So we interpret it no matter what as a positive angle. So if you want to look at it as a positive angle, you have to kind of go to this way around. But in geometry problem, we interpret all the angles pretty much as a positive. So they don't indicate direction, so you should look at this as an initial side, and that's the terminal side, like that, right? So these arc length they're talking about is this one in here. That's the arc from point A to point B. Usually the center is denoted by letter O. So from A to B is the arc length. So that arc length is denoted by little s in there, right? You see the difference between the length of this arc versus the length of a line segment joining A to B. You see that difference, right? Straight line from A to B versus curved line A to B. And this curved line A to B will be slightly longer than the straight line A to B, right? Yeah. So what is the formula of S in here? That's the what we want to look at in here. This the formula is the radius of this circle, which is usually given R, times theta, where theta is in what? Radian mode. Yeah. You have to use radian magnitude to apply this formula. Isn't that neat? R times theta. It's very simple, right? I'm sure this is the very motivation to switch to the formula to the radian. I mean the unit to the radian. So that is quite simple in here. All right. This is usually the formula. But I'd like to make some clarification on this formula. For example, if I'm looking at this odd-looking Pac-Man kind of shape of arc, right? So it's not the other one. This is usual shape of arc, this kind of oversized arc, but it is called a still circular sector. And how do we particularly indicate the angle theta to be here on that side? Something's more than 180 degree. Then this is a circular sector, and this is a radius in here, and this smaller part is missing and the larger part is a circular sector. So if the arc length S here is represented still by R times the theta, it's the same thing. It's a little odd shape, but this formula still applies to that. Okay? Another extreme case would be starting in here, ending it there. So full complete circle, right? So arc length here is a center O, arc length here, would be still r theta in here. And theta here is the complete one revolution. What is that actually, Nat? One complete revolution. What is theta? 2 pi radian, right? But we use just that 2 pi. It's r times 2 pi. If we just apply that formula, so rather known as 2 pi r. Does this agree with something you know about circle? 2 pi r is the length of a circumference of a circle, right? So that is a special case of an arc length of a circular sector when the subtended angle is one full rotation 2 pi radian. Does that make sense? Yeah. So these are some cases you're going to look at, but most of the time circular sector we mean by slightly smaller circular sector shape like this. All right? So that's the formula. We're going to go through some of the examples to get used to this formula and think about later why the formula arrived like in that form r theta. Okay? That's the theory part. We want to look at that so that we have easier time to understanding and memorizing this formula. It's just to make sure you understand that none of these formulas is given in class, and you have to practice and think enough about it, so memorize it and thinking about and how it works and things like that. Okay, so here's some example. Alright, I am hiding the formula, just like last time. Part A, find the length of an arc of a circle with a radius 10 meters that subtends a central angle 30 degrees. So I'm going to, what's a little exercise, a partial exercise in here. Once you get used to this, it's not necessary to sketch the situation, sketch the sector, right? But it always helps you, always help me to understand what is that you're thinking when you're applying the formula. So if there is a mistake along the way, if you have nice picture and organize information properly, then I say, hey, this person thought properly, I'm going to give half or 2/3 of a credit because I can see the evidence that examinees are thinking clearly in here, right? So if time, you have to think about and balancing out what to write down in a solution. But does it look like 30 degree roughly, right? Subtends angle 30 degree. So I'm going to sketch like this. 30 degree slice of pizza. That's one way to think about it, right? So what else you know about this thing? I want to radius 10 meters, right? So here's a radius. It's going to be 10 meters. Large pizza. 10 meter. All right, and that's not straight line. This is a little, part of a circular sector, and that's what we're looking for, right? Okay. So the formula of arc length, let's think about the formula of arc length here. S equals, what was the formula? Radius times magnitude of angle in radian, right? So this is a formula. We got 10, right? We want to use the magnitude, and we're going to end up in what dimension? This is going to be a length or area or weight. What is that going to be that we're calculating? S. Length of arc, right? What's going to happen to the meter? Change to meter squared or meter cubed? Remains as a meter, right? So length. So it's going to be R 10 times magnitude in radian theta. Meter is going to be the answer. Right? Your question is, what is that theta? The answer is not 30 degree, right? No, so let's write that down. We have 10. We're going to multiply theta, and that's the answer. So what is the theta? 30 degree. That's what I gave you, right? But it's in a degree, so how do you convert this 30 degree to radian? We're converting into radian, right? So there's this factor. What goes in numerator? Pi, and denominator 180. That's the universal factor in there. That's radian. What do we multiply? That magnitude in degree 30 here. And that's going to give you the radian measure, right? So how does they cancel? pi over 6 radian right there. So now you wrote theta in radian. We just use this magnitude pi over 6 there. So we'll come back to arc length S 10 times. What is the magnitude in radian? Pi over 6, right? And what is the dimension? Meter. Yeah. So in exact form, how does this 10 and 6 cancels? 5 with a 2 in the 5 there and 3 there, right? Okay, 5 pi over 3 meter. Who wants this thing in the bottom? You know, we usually want in whatever decimal number that's more meaningful information. So this is probably what web assign wants at this stage. But what we really want is the numerical answers. Can somebody actually calculate this for me? So let's make sense out of this. I have 10 meters to the side. And according to that picture, is like just about half. That makes sense, right? Sometimes if you did something wrong, the wrong magnitude and wrong dimension, you use magnitude and degree, this will be way off. And carefully draw the picture, and usually it indicates that if you have 50 meters, that doesn't look like 50 meters, right? If this is 10 meters, it's discussing about half of the size, things like that. So sketching it carefully really helps you to make sense out of your answer. You got it. All right? Let's read the second part and see. Let's decide if we're going to make this one an exercise. The central angle theta in a circle radius 4 meter is subtended by an arc length of 6 meter. Find the measure of a theta in radian. Okay, they gave you arc length, not the radius, I'm sorry, but they gave you the radius, but they want you to figure out the measure of the angle. All right, it's about slightly reorganizing this equation. So let's make this one as an exercise. Right, here's part B is your exercise. How'd it go? First, I wrote the formula S equals r theta. Well, right now this is what we're doing, so it's automatically consider that. But think about the situation that you have learned a lot more things, and all of a sudden this question showed up in the test, and you should be able to relate that by looking at this information. I'm going to consider this formula: S equals r theta. Arc length, radius, subtended angle. There's a formula that relate these three quantities, right? So you think about S equals r theta. Put yourself into that situation. So this is probably the hardest thing, to come up with a first liner. Always, that's the hardest thing in the test. Once you do that, you have arc length given 6 meter, radius given 4 meters, and angle theta is what we don't know. So we put it into all the information here. This one becomes an equation in one variable, right? And algebraically you can solve it. And here 3 over 2. Now the question is that this angle theta is supposed to be 3 over 2. So where is a pi? Am I supposed to put pi in here and label radian, or just leave it like that and the radian? First or second? Which one is the correct answer? What's that? Yeah, leave it like that. This itself is the magnitude. You don't put extra pi in there. This is it. So you just put radian right there. 1.5 radian or 3 over 2 radian is the exact answer. Right? But we want to know, here is a 10 and here's a 4 and 6. What is the actually angle? Well, so if you really want to have a shape of that, sector, you want to convert this one into degree, right? So I'm going to do that extra thing in here just to get a sense of it, the shape of the sector. So how do you convert this radian into degree? Right, 180 times divided by pi, right? And it becomes degree, right? So let's convert this one into, this is not wiggly symbol, this is exactly equal. Would you agree? So sorry about this thing. This is exactly 3 over 2. Nothing happens to that part, and you multiply that. So let me have this number 1.5 times 180 divided by pi in decimals, please. The number of this one? 1.5 times 180 divided by pi. Right, so I'm just going to take 85, give you a rough idea. It's almost 90-degree size of a sector, right? That's the we have. Right, this is our exercise again. Find the length of the arc S in the figure where they gave you information like this. S is the red part, but they gave you the angle not quite right for that part S. You have to figure out what the angle for that subtended arc for. Okay, I think the key thing is that you figure out the angle for that longer circular sector, which is 360 minus 140, right? 220 degree. This is 220 degree. That's what you're supposed to use. If you use 140, you will be calculating arc length of that side there, right? Okay? So 220 converted to radian, the answer was 11 pi over 9. If you cancel the common factor, cancel 0, factor of 2, 11 over 9 pi, multiply the radius, which is 5, so 55 pi over 9 is the exact form of the length. They didn't give the dimension for the radius, so you will keep it as like this. In the test, I don't usually mix up a meter and centimeter, so it requires converting those things, but occasionally there are the Weber sign problems that you have to go through the conversion, for which you have access to internet, to conversion formula, things like that. So I usually never do that in my test problem. You stick to same dimension all the time. Except 60 seconds and converting to minute, things like that. Something like that. But I thought that's common knowledge. Why on earth the sector S is given like this? It relies on some of the fact that whose answer is actually quite profound, so I'm not going to answer that. But here's why. Why, as is r theta, is a good explanation they have in the book, so I'm going to use it. So it relies on the following idea. Here is a full circle with the radius r, and its circular sector, its arc length, which is circumference of the circle. What was it again? S1, the formula. If you're looking at the entire circumference, what was the formula for 2 pi r? Okay, that's the thing. And here's a circular sector, the same radius, theta is here, r, and we're looking at S2, right? This is a slightly smaller circular sector. So here's the intuitive approach to this one, is that they realized the ratio between S2 and S1. S1 is the full copy of a circle, the circular sector, and S2 is a smaller copy. And they believe this must be equal to the angle for the full rotation, which is 2 pi, and angle for this smaller sector is a theta in here. Because of this perfect symmetrical shape, they believe the ratio of this two length must be equal to the ratio of the two circles. Because if you think about half of the full rotation, 1/3 of the full rotation, 1/5 of the full rotation, if you divide this sector into 10 pieces, 10 equal pieces, 7 equal pieces, this kind of makes perfect sense. In general, you have to kind of refine it into very tiny pieces to make sense out of it, but this idea makes perfect sense when you divide it into 100 pieces, 5 pieces, and things like that. So this is the idea. The ratio between subtended angle must be equal to the ratio between the circumference and the area arc length of a circular sector. That also goes to the area as well. So they believe these two things are the same. It's not a rigorous proof, but it helps you to understand where the formula is coming from. S2 is what we are looking for, what we want to calculate. So I will leave it there. But we know about S1, the entire length of a circumference is 2 pi r, right? And theta is there, and 2 pi is the full angle measure of one rotation, one revolution. Okay? So if you instead use a 360, instead of using the radian measure 2 pi, if you use degree measure, you're going to have 360 in here, right? 360. Then there's no nice neat cancellation between 2 pi r and 360. So they rescaled it to 2 pi so that this pi goes away and formula is neater. Okay? So you can see that 2 pi and 2 pi cancels, right? Because that's the measure of a full one rotation. So what does that become? S2 is, if you multiply r both sides, it's r theta. So if you keep your theta in radian measure, the length of a circular sector with subtended angle theta is simply r theta. It's a neat formula. It came from the idea of comparing the ratio of the circular sectors and the ratio between the subtended angles of the two things. Okay? Although it's not perfect proof, gives you a clear idea using the intuition. That idea goes the same for circular sector as well. Okay? This angle gives you an incredible ability for us to measure large object. That's the whole idea of this trigonometry at the beginning of the trigonometry. And then we move on to the motion, and it becomes more sophisticated and complicated. But let's look at this neat example. Any question about this idea? All right. So that's the formula r theta. We're going to look at circular sector as well. But here is so this. I was in the second picture. So I'm going to use this example to explain the applications of this angle measure thing. It's a neat example if you haven't seen it before. All right, let's read this problem together. This is the Earth, giant size, and there's two cities, and Syene and Alexandria, and this path is directly toward to the North Pole, right? So this guy measured at the one point in this city Syene, the sun rays coming in directly above. Maybe you can put a long stick and see that the shades of the stick is almost none because it's right above. That's one way to measure that if the sun rays are directly above the ground. But making it perfectly perpendicular to the stick is kind of another tricky thing, right? And I heard that you can put the water, large area of the water, and how the water surfaced out gives you an idea about this is the perfect flat side, and you can sort of construct a perfectly perpendicular stick to the direction of a gravitation, things like that. So suppose that happened, and they had cell phone back then. So this guy in Alexandria communicating exactly at the same time, they did the same thing, but it has little shadow. You can see that sunlight is coming in. It's exactly the parallel shape, and the shade creates. He could measure the angle created by the shade is a 7.2 degree. Does that kind of make sense? All right. So the reason the sun rays is perfectly parallel here is that distance between the Earth and the sun is astronomical unit. You can think about it, if you're here and the source of a light is right close to each other, and let's say a large object in here, very tiny light bulb is here, you can see it's not parallel. How the rays are coming in is definitely not parallel. But if it's really, really far away, then you can imagine here's a giant sun, here's far, far away, then it is almost, you can kind of experiment, is almost a parallel. So slight different angle, and here at that point and that point it can be ignored. So that's the one measurement you can possibly do, and the distance between these two guys is 500 miles apart. All right, you could have done that without a cell phone. At one point of the year they do that, and exact the same point of the next year they traveled and stayed there and 500 miles above and figure out that's exactly the same point of the year, and then they did another measurement, and you have these two things. And they're claiming with this much of information you can handle, you can measure the radius of the Earth, right? So let's do that together. Kind of shows the power of this idea of thinking about an angle. All right. You see a circular sector? That's the whole thing. We've been talking about the circular sector. So where's the center of the... Although it's actual three-dimensional shape, if you slice the Earth, and you can imagine that imaginary line there, the circular sector. This is the center of the Earth, right? And there's many, many miles like that. And there's the, what is that called? Longitude, latitude. That's a longitude, I think. Along this same longitude. And there's an extended line in here, and there's an extended line. And there's another extended line. These two lines are parallel to each other. I think it's international symbol of double arrow indicating these two lines are parallel to each other. Okay? And what else do we know about this point A and point B in here? This angle in here, right? What is this angle? They gave a 7.2 degree. It's the angle. We want to know about the circular sector. What do we want to know about circular sector? That formula S equals r theta, right? So we want to know about this arc length S. Do we know about this arc length S? 500 miles. How about the radius here? Not yet. That's the whole question, right? What is the radius of the Earth? And this angle theta is in question. At this point, we don't know. But some angle is given, and you have to think about the relationship between this angle theta and that angle 7.2. This is extended line, not crooked line, right? The way in the cyan, at that point, this kind of radius line is perfectly extended to this ray of a sun ray in there. So this whole line and that whole line is kind of extended. So let me redraw to give you an situation. Here's a 0, and here's A, and here's B, and here is parallel line there, and this is extended line, the parallel line there. And that angle is 7.2 degree. This redrawn picture is kind of part of what we have drawn exactly, right? These two lines are parallel to each other. Don't you think that this copy and that copy is kind of congruent copy, right? Because of the parallel line. So what do you think about what your intuition says about this part in here? That's exactly the same 7.2 degree, right? So these kind of location across this parallel line gives you exactly the same angle. Make sense? So we know what theta is. From there we conclude theta, right? What is it? 7.2 degree. So let me resketch that circular sector there. Long circular sector. This actually a lot bigger than 7.2. Let me exaggerate so that I can write things in. And what is the arc length? 500 miles, right? Whatever you get for the radius is going to be in miles. Okay? So why don't we go ahead, and we've done problem like this before in the previous exercise. I want you to try this one. So I guess in the Weber sign problem like this, they want, I think they didn't say that, but we're going to round it up to the miles. Didn't care about point whatever the miles. All right? So use your calculator. Get rid of pi's and complicated. Just get a decimal number for this one. All right? So what is r? So here's a more mathematical setting of the problem. I want to make the rest of the part exercise. Figure out r in decimal approximation in miles. That's your. All right, we eventually use this s equals r theta, and from earlier examples, you know theta has to be in radian. So first thing I did this time, looked at 7.2 degree, and turned it into radian and decimal, since we want approximate answers. So it was 0.1256 radian. That's the measure of the 7.2 degree. And put it into this arc length formula, s equals r theta, 500 miles, r unknown, on 0.1256 magnitude in radian. So you solve for r, you get 3,900. As far as I know, this is pretty close to the actual measure of the radius of the Earth, 39. All right. Next, we're gonna actually calculate this. Earth rotates around one rotation per day. Knowing this radius, you can kind of calculate how fast this equator thing is moving, in what speed the points on the equator is moving around. That was turns out it's actually faster than the speed of the sound. The way that around the equator is rotating around, the speed on that spot. If you're looking at the moon and how fast it's rotating, that's faster than the speed of sound. I think it's surprisingly fast. Some of the example I had in mind to go through for arc lengthening. Make sense? Right. Let's look at second formula. What would be the second formula? Area of a circular sector. Right. So it's the area of a circular sector. The shape is the same. Here is a center, O, and here is perfect circle here, and here's a sector, and in general this can go over 180 degree Pac-Man shape like that, and A to B. We use P to Q, then I want to use A as area, so let me change the point to P to Q here, and subtended angle theta here again, right, and radius r. What is the area A? Usually A stands for area. The formula is half times r squared theta. That's the formula, period. For some reason, r theta is very simple. Nobody forgets this r theta. But this formula turns out in an incredibly different shape in the test. So it seems like it confuses students, whether there's a 2, square goes the other direction, and things like that. Because it's a square, you know the dimension is like a mile square, a meter, squared meter, things like that, right? That's one indication. You got to put that r squared in there. R is the length, got to be squared. Theta in this scenario usually doesn't get squared. So that's one of the things that I want you to remember. And maybe if you forget this 1/2 factor, but think about the area of the full circle. What is the area of the full circle? Not this circular sector. What is the area of the full circle? Area of a circle. Anybody remember the formula? There is r squared there, right? Because it's area. But what is the other proportional? It's a pi. Pi times r squared, right? If it's a circle, it's not the particular sector, but can you look at the full circle as a circular sector with subtended angle theta? What would be that theta for the full circle in this case? Full one rotation, right? 2 pi, right? 360 degrees, so 2 pi. So I want you to stick that 2 pi in here, see makes sense. 2 cancels and pi r squared. Does that make sense? So if that subtended angle is 2 pi, that goes all the way around, making a full circle. Let's apply that formula here. Half times r squared times angle in radian measures at 2 pi. Therefore, 2 cancels and gives you pi r squared. That formula checks with what you know about the area of the full circle, right? Maybe this connection will help you remember or correct your formula if half wasn't there or 1/3 is there, have to be the wrong. Okay? But this is just simply the formula. Half times r squared theta. All right? The way the example works is quite similar. It's just a slightly different formula, an area of this one in here. So this time, I'm going to explain why the formula is derived like that first, and then we're going to go to example. So y of a circular sector A is 1/2 times r squared theta. All right? What was the idea? Remember the idea? So let me give you these two things. A full circle with radius r, what is the angle there? 2 pi radian, right? You go around all the way. That is going to be area A1. What is that area A1? Pi r squared, right? And the second thing we want to compare is the circular sector. And there's this angle theta, which is not 2 pi, smaller, and its radius r. And area of this one is denoted by A2. Okay, before it was S1 and S2. But remember what we did to this two quantity? We took the ratio, right? Took the ratio of this A2 to the A1. And we compare that ratio to the ratio of what? The subtended angle. Think about slicing into 4 pieces and 5 pieces. So what is the angle correspond to A2? Theta in radian, right? What is the angle correspond to A1? It's 2 pi in radian, right? So the ratio of these two things must be the same because of the perfect symmetry all around the center. So they believe this must be the same there, right? This is why we want to figure it out. And this theta in A1 is something we can figure out. So here's A2. What was A1 again? A1 is the area of the full circle. It's a pi r squared, right? And theta is there. And 2 pi is the angle full one rotation. A2 is what we want to solve for. But first we can cancel pi, right? This time 2 did not cancel. Because the area of the one full circle does not have 2 in it. Area of, the circumference has 2 pi r and 2 in it. The 2 also cancel. So let's solve for A2. Is if you multiply r squared both sides, r squared theta divided by 2, pi is gone, right? So that can be rewritten half times r squared theta. That's where the formula came from. Okay? Alright, I'm going to save this one quick. We'll have 2 minutes break, and we'll continue with more examples of circular sector and area. Alright, so here's examples and problem. So I'm going to make this example exercise. The procedure is the same with the arc length. I think you can do that. So that's our exercise actually. If that was easy and if you could do it quickly, then try to do these extra problems I wrote there, 61 and 62. Alright, how was the first one? Example 5, was that alright? That was not so straightforward. Actually straightforward. You're just calculating area A, so you plug it into in here. The area information, just first you have to convert that angle 60 degree to radian, and that's it. So R was 3, so if you square it, it's 9. Theta in radian, it was pi over 3. So altogether in exact form, so 3 pi over 2 meters squared is the answer for the example 5. Okay. Do you have any question about example 5? Is that okay? Alright, so on 62A was like this. They gave you the angle. If you read the question, find the radius of each circle. Area is given 12. So you're not computing the area, you're computing the radius, missing one information, which is radius. That's what we're doing. So let's look at, this is a picture. The theta is given 0.7 radian already. R, we don't know. And area here is given 12. Okay, theta is already in radian, so I'm not going to convert anything. Write down this information. Formula, area is 1/2 times r squared theta. Then plug in all this information, and it becomes one variable equation. Area here is 12, and 1/2 r squared, we don't know, and the magnitude angle in radian is 0.7, so I plug it in here. Right. From here, it's doing the algebra. I think that's the hard part. Okay, first I simplified 1/2 and 0.7. So 1/2 is there. 0.7, I interpreted the 7 divided by 10. to do the calculation exactly. Does that make sense? 0.7 is 7 divided by 10? Right. So there's no common factors. I combined together 7 divided by 20. So I didn't touch 12 on the left-hand side. I just simplify right-hand side like this. 12 equals 7 divided by 20 r squared. And we want to know r squared. So first you solve for r squared. Then you multiply the reciprocal both sides. So it's a 12 times the reciprocal of 7 over 20. Multiplied it here. Altogether is 240 divided by 7. But that's still r squared here, right? So for r, you have to put the square root. When you algebraically solve equation, you always have to think about the possibility and the plus and minus. Sometimes it really matters. And here, r is a positive number, so obviously you choose the positive sign of a square root when you solve squared equals something. But sometimes you have to consider negative. Think about if that makes sense. So this is an exact form. Root 240 divided by 7. This shape of the answer is called exact value, right? Maybe Weber-san wants this, but if I ask you to get an approximate value to 4 decimal places, and you use your calculator to convert that into down to 4 decimal places like this, hopefully using this wiggly symbol, distinguishing this is, not exact approximate value of r. Does that make sense? Two things. First, having a correct idea. Second thing is carrying out this algebra to get the correct answer.